Hello, everyone, and welcome
Hello,
to the
everyone. Can you
second
hear me?
session of our Spring 2026 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, this is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, we'll have two presentations. First, Muhammad Ishfaq will be presenting his work on the use of fiber-reinforced polymer composites for strengthening civil infrastructure. And then Victor Calderon will be presenting his work on deep reinforcement learning for urban rail flood recovery. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions as usual or send them using the chat feature, and I can read them out loud. I'd like to point out that this meeting is being recorded and will be made available shortly after. Thank you all for attending today, and with that, I will introduce our first speaker for the day, who is Muhammad Ishfaq. Muhammad is a final year PhD candidate in structural engineering at the University of Delaware. Muhammad completed both a bachelor's and a master's degree in civil engineering at the University of Engineering and Technology in Peshawar, Pakistan. He is interested in strengthening reinforced concrete structures using fiber-reinforced polymer systems, with an emphasis on large-scale experimental testing and nonlinear finite element modeling. Muhammad, whenever you're ready, you can share your screen and you can begin your presentation.
Okay, thank you. Thank you for your introduction, and let me share my screen.
Nice.
Yes, so are you able to see my screen?
Yes, we are.
Okay. Hi, everyone, and thank you for having me. As mentioned, my name is Muhammad Ishfaq, and I'm a final year PhD student working under supervision of Professor Yuval Tatar at the Department of Civil Construction and Environmental Engineering, University of Delaware. My presentation topic is strengthening of civil infrastructure for enhanced resilience using fiber-reinforced polymer composite material. Specifically, I would be talking about URAPs, which are used as an anchor or as a supplemental shear reinforcement in FRP strengthening applications. So let's dive in. So my presentation has four parts. First, I will explain the background of my research topic. Then I will discuss the methodology of our experimental procedure, then results, and finally conclusions. So we all know that American infrastructure is old and it's crumbling, and you cannot build a modern economy on a crumbling infrastructures. For example, bridges crumble due to age, extreme weather cycles, and overloading due to growing populations. Let me share some statistics. According to US Department of Transportation and American Society of Civil Engineers reports, there are around 617,000 bridges across the United States. And of these, more than 45% are over 50 years old, and around 46,000 bridges are classified as structurally deficient bridges. Now, what should we do with these old bridges? Should we dismantle them or replace them with new ones? Of course not. We need economical solution to strengthen the existing bridges even without disrupting their functionings. And also, if we repair or retrofit these old infrastructure, we can save so much in terms of material, cost, energy, and even carbon emissions. So these highlights the importance of bridge strengthening and rehabilitations. So there are several methods have been used for strengthening the existing infrastructures. In these methods, one is concrete jacketing, in which we add a reinforced concrete layer to the existing structures. Likewise, in steel plate bonding, we add or we bond steel plates using anchors to the existing structure so to improve its performance. But these are old and traditional techniques, and they are labor intensive and they are less efficient. And we need efficient techniques using smart material and smart techniques, and one of them is FRP strengthening. So now what is FRP? FRP is a composite of fibers and polymers. And if I give you example of reinforced concrete, which is also a composite material, in reinforced concrete, steel rebars used as a reinforcement and concrete as a matrix. So likewise, in FRP, polymers is used as a matrix, and fibers, which are in order of micromillimeters, they are used as a reinforcements. These fibers can be from glass, they can be from carbon or aramid. These are various type of fibers which are used in the FRP composite. Now the question is why we are using FRP. So it has very lightweight and it has very high strength, and it is also corrosion resistance as compared to steel. Like if I compare with steel, so it is 10 times stronger in tension, and likewise it is 10 times lighter in weight from steel. FRP is used in construction industry in various forms, like it is used in as a rebars, as an alternative of steel rebars. Likewise, FRP pull two dissections are used to replace W section, I section, and S sections. And it is also used as a fabric sheets, which are bonded to the existing structures for repair and strengthening procedure. And this is the topic of my presentation. So in these pictures, you can see how the FRP sheets, which are of in order of millimeter thickness, they are bonded to the existing surface of the structures. And by this way, you can improve its axial performance, its shear performance, and its flexure performance. And in these images, you can see how the FRPs are installed around the column, in the girders, and you can also see the U-shaped strips of the FRP, which is called U-wraps. So there is a problem associated with the use of FRP, and it's called premature debonding. Like in this image, you can see we have a bridge girder and the FRP is bonded to the tension side of the girder. But once the load comes, it's prematurely debonded. And this debonding occur at a very low stress level, even at around 50% of the strength of the FRP. And let me show you a clip in which you can see how this debonding happen. And in this video, we tested a beam in our structural lab. And let me play the clip. And once the load comes, you can see how it is debonded using sudden failure from the existing surface. Now, how we handle or how we mitigate debonding. So various kind of anchors are used, and the two popular one are U-wrap anchors and fiber anchors. So U-wraps, they are also used as a shear reinforcement for strengthening the shear performance of a girder or beam as well. And they are U-shaped strips of CFRP, and which are bonded to the soffit and two side faces of the girders or beam, and they are acting as an anchor for the flexure CFRP and as well as for shear reinforcement. The second anchor is fiber anchors, and they are bundle of fibers which has two parts, dowel and splay. The dowel parts are inserted into the concrete using already pre-drilled holes, and the splay parts are bonded to the existing FRP, and that's how we can introduce a mechanical anchorage between the substrate and the CFRP. And how they are installed in the girders, you can see in these images, they are installed like this. We also have codes and guidelines, and you know that in the construction industry, we need codes and guidelines to protect people from poor construction and design. So for the FRP, the recently published guideline is ACIA 44013, which is published in 2024, and this is the first code for the FRP application in construction industry. Likewise, the AASHTO code is the updated version of the AASHTO code is also published in 2023. Now, these codes provide how we can compute the contribution of the FRP in the existing structures. So you can see we can compute easily using the stress and the cross-sectional area of the steel, and we can compute the moment capacity of the beam. But if we add the CFRP on the tension side, so we can add the contribution of the moment contribution of the FRP to the existing beam as well. And for this, we need stress in the FRP. And to compute stress, you can compute stress from the strand, and this strand is called debonding strand. So this is an empirical equation which you can utilize to compute the strand, and from that strand, you can further compute the stress to compute the moment capacity. Likewise, the ACI provisions is also available for the shear, supplemental shear reinforcement of the U-wraps. And for the U-wrap contribution of for the shear is using the same truss model which is used for the steel. And in this model, the only variable is the strand in the FRP, and that strand is computed using these equations. And these are functions of concrete strength and the height of the UREFs. So now, what is the research gap? So I discussed about UREFs. Like UREFs, they are used as a anchor for the flexure FRP, and they are also used as a supplemental shear reinforcement. But the question is, can UREFs serve two functions simultaneously in a beam? Like there might be instances in which a beam might be deficient in both shear and flexure. So there we can utilize UREFs to enhance flexure capacity and as well as the shear capacity. So this is the research gap which is not investigated in the existing literature, and we come up to find the answer of these questions. So to fill this gap, we design our study with two objectives. The first objective is to investigate the complementary shear strengthening and anchorage effect of UREFs in reinforced concrete beam strengthened with externally bonded CFRP laminates. The second objective was to make design recommendation for the efficient use of UREFs as a supplemental shear reinforcement and anchorage. So to achieve these objectives, we come up with a test matrix of 18 large-scale reinforced concrete beam. We divided the beam into three groups. The first group is called NS, which is with no stirrups. The second group is with minimum stirrups, which is number 2 at 8 inches center to center. And the third group we designed with sufficient shear reinforcement. So they just fail in flexure, and the reinforcement was number 4 at 8 inches center to center. So this is the drawing of the specimen which we tested. You can see we have a 14 feet long. It is 16 feet long, and it is tested on a 14 feet span. We use the typical concrete with 4,000 psi strain, and the reinforcing steel was grade 60. Then we add 2 ply of CFRP on the tension side. And further, to anchor the existing flexure CFRP, we install UREFs. And these UREFs and the flexure CFRP, they have the same properties, same material, and you can see the mechanical properties of these material on the slide. And in some beams, we also further anchor the UREFs using fiber anchors to enhance its performance. These are the drawings of the control specimen in each group. In the first group, we have no stirrups. In the second group, we have number 2 at 18 center to center stirrups. And in the third group, we have number 4 at 18 center to center. These are the drawings for the specimen in which we use various configuration of UREFs. So for the group A and B, in which we have minimum shear reinforcement and no stirrups, we use same configuration of UREFs. You can see we have 0 U mean, no UREFs, then we have single ply UREFs, then we have 2 ply UREFs, and then we have anchored single ply and 2 ply UREFs. In the right side, you can see group C specimen. In these specimen, we only install UREFs without any fiber anchors. And the combination of the UREFs, you can see again, we have single ply, 2 ply UREFs, and we also introduce reduced height UREFs and full UREFs. We tested these specimen in typical 4-point bending setup. We installed beam in inverted orientation, so to utilize the digital image correlation for full field strand mapping and displacement. Now I'm presenting the results, and I will go group wise. So I'm starting from group A, in which we have no stirrups. And on this plot, you can see the shear, the load displacement plot. And the first specimen, which is control specimen without any UREFs, and you can see its load displacement plot. And on the right side, you can see once it is failed in a typical diagonal tension cracks, and you can see the crack pattern as well. Then we added single ply UREFs. By adding single ply UREFs, the capacity is increased from around 40 kips to more than 60 kips, and the failure mode is UREF debonding followed by typical diagonal tension cracking. Then we add second ply. So by using second ply, we didn't achieve any considerable enhancement in shear capacity, and we also achieved the same failure mode UREF debonding followed by tension cracking. Then we install single ply UREFs with anchored UREFs, and in this case, we also achieved the shear failure, and the capacity was enhanced a little bit by 10%, and and we achieved the typical shear failure as well. Then we further add the two-ply UREFs with fiber anchors. In this case, we transition the beam from it passes the yield point, and the capacity is further increased from more than 80 kips. And we were able to achieve up to 95% increase in capacity by using anchor two-ply UREFs. And this was also again failed in shear. Now I'm moving to the second group. In second group, we install number 2 stirrups at 18 center. And now you can see the load displacement response of the control specimen. We have achieved more than 45 capacity, and the typical diagonal tension cracking failure mode on the right side you can see. If then we add the single ply UREFs, by adding single ply UREFs, the capacity was increased, and we also achieved the same failure mode. Then by adding two-ply UREFs, we also achieve the capacity enhancement, but the capacity enhancement as compared to single-ply UREF was not significant. And the failure mode, you can see again, a UREF debonding followed by tension cracking. Now then, when we use the anchored single-ply UREFs, so in this specimen, the failure mode changed from shear to flexure, and you can see we achieve the flexure failure, and the flexure failure was the flexure CFRP rupture. And you can see the capacity was also considerably enhanced. And also by adding the second ply anchored UREF, we were again achieved the same CFRP rupture failure, and the capacity increased was around 105% as compared to the control specimen. Now I'm moving to the third group. In the third group, we have only flexure control specimen. So this is the typical load displacement plot of the control specimen. And you can see we have a trilinear plot, cracking followed by cracking, and then we have the yielding of the steel as well. And this is the specimen with 0U, and this has only a flexure CFRP. By adding flexure CFRP, we increase the capacity up to 80 kip, but the failure mode is premature ICD bonding, and you can see we didn't utilize the full capacity of the CFRP. So then we add the UREFs. So by adding UREFs, we increase the capacity, the moment capacity of the beam, and the failure mode is also changed from the ICD bonding to the rupture of the UREFs. And then further, by adding two-ply UREFs, we were able to achieve, we were able to mitigate the ICD bonding failure mode. And in this case, the failure mode was UREF debonding instead of rupture. And in full REP debonding, we were even able to achieve the concrete crushing failure, and the capacity was almost the same. And in the last specimen, in which we reduced the height of the UREP to optimize our design, in this specimen, we also achieved the full capacity of the specimen, and the specimen failed by concrete crushing. And in this group, we were able to achieve up to 27% increase in moment capacity. So this is the overall summary. On the left plot, these are all the shear control specimen. And in this plot, you can see we calculate the contribution of each component. The black bar represent the shear capacity of the specimen, and the blue represent the concrete and the steel contribution, and the green represent the FRB contribution in shear for each specimen. And you can see for the anchored two-ply UREFs, we were able to achieve even higher shear contribution from steel and concrete. On the right plot, they are all flexure control specimen. They are all fed in flexure. And in these plots, you can see by adding UREFs, we were able to increase the strain in the flexure CFRP, like for the 0U specimen in which there was no UREF, as compared to this specimen, you can see we were able to achieve up to 55% increase in the strain, and we increased the performance of the UREFs. We also we compare the design and the experimental capacities. So you can see, like, using the existing code guidelines, if you compute the capacity and compare with the experimental, so all the specimen capacities are conservative. So the current design guideline, they have no provision for the UREFs or for the anchors. So what we did, we introduced an anchorage coefficient which is called Ka, and the value of this we assume 1.4. And by using this coefficient in the existing model of the ACI, and within we compute the capacity of the anchored specimen, and still the results were conservative. So it means we can introduce this coefficient in the existing model for further revisions. So these are the final conclusions. So UREFs can effectively serve as a supplemental shear reinforcement while providing anchorage to reflect the CFRP. And we also observe in specimen with number 2 stirrups, which transition from shear to flexure failure. And in that specimen, we were able to achieve shear capacity up to 95% and the moment capacity up to 35%. And in flexure control specimen, all specimen achieve almost same capacity, but the failure modes was changed from IC debonding to the UREF debonding or concrete crushing, and we were able to achieve up to 27% moment capacity enhancement. And we also observed that UREF anchor with reduced height perform as well as the full height UREFs. And finally, if we introduce the anchorage coefficient to the existing model, still we will be able to achieve the conservative results. In the end, I acknowledge the sponsoring agency, which help us financially and as well as technically in this research project. With this, I concluded my presentation, and I'll be happy to answer your question. Thank you.
Thank you, Muhammad. That was a great presentation. Let's open it up for questions from the audience now. If anyone has a question, feel free to. Jürgen?
Yeah, I would have a question. Yes, thanks for this very great presentation. Since a lot of work went into this testing. I have one question for applicability into the, I guess, real world. I assume it strongly depends also on the surface imperfection where you try to glue these things or how to fix it on the existing beam. I assume in the lab experiments you have perfect specimens, but when you go outside, there might be surface imperfections or other failures already existing on the beams. How would your performance behave in such situations?
Yeah, so it is a very good question. And to explain this, so we don't apply the FRP directly on the surface. First, we do prep work. And for the prep work, we first remove the debris, the loose particles, whatever on the surface we have. Then we do sandblasting to roughen the surface to provide a good bond between the FRP and the existing structure. And after that, we do the FRP applications. And in some cases, for example, if our structure is already deteriorated or it needs repair, so first, before installing the FRP, we do some repair work and we create a smooth surface, and then we apply the FRP. So yeah, so it requires a very smooth surface. You cannot apply FRP on a wavy or rough surface.
Thank you for clarification.
Yeah.
Yes, yeah, thanks.
Any other questions from Muhammad?
I just want to ask a quick question regarding particular. Are you thinking about cyclic tests? Because when I think about cyclic tests, it's because of earthquake applications in particular of this kind of reinforcement. So it's just, are you thinking about it or maybe not? It's like
yeah,
a
so
particular use of
earthquake,
reinforcement.
like CFRP, this is also used in earthquake-prone areas, and for that, of course, you need to check its performance in fatigue or cyclic loading or earthquake loading. You are correct, but we tested this in quasi-static loading, and we didn't consider that. And there are a lot of researchers and they are working on this area as well, and there is a lot of research going on. But we didn't work specifically on for cyclic loading, the performance of the CFRP. So sorry, I'll be not able to answer your question.
Anyone else has a question for Muhammad? Otherwise, thank you once again. That was a great presentation, and we can now start with the second part of the session. So I'm going to introduce our next speaker, who is Victor Calderon. Victor is a student in civil engineering at Princeton, where he is advised by Professor Jürgen Hackel. Victor holds a master's degree in civil engineering with a specialization in structural engineering from Stanford, where he was part of the Stanford Urban Resilience Initiative. His research focuses on physics-informed artificial intelligence and infrastructure network resilience. Victor, whenever you're ready, you can share your screen. Oh, you already have. and you can start your presentation.
Okay, thank you everyone for attending this meeting. I'm going to talk about another kind of reinforcement. And also my background, as well, as Pablo said, is in structural engineering. So there's been a lot of time that I've been practicing in structural engineering, but hopefully this topic is going to be also of your interest. So what I'm going to talk about is reinforcement learning for flood recovery in urban rail systems. Please keep your questions until the end of this presentation. Hopefully I'm going to be able to answer all of them. Yeah, starting with the presentation, I wanted to talk more about the context we are living in. So climate change has increased the number of times we see flash flooding events happening around the globe. So flash flooding events usually affect more to infrastructure, well, distributed infrastructure systems, for example, metro systems. So 2021 was a very particular year because we saw three of the most important metro systems around the globe being affected by these flash flooding events. We saw it happening in New York City, in London, and Hong Kong. So when this flash flooding happened, and affect or disrupt this metro system, not only disrupt the normal functionality of the system, but also endangers the user of these metro systems. So what can we do in particular to improve the flood resilience of these metro systems? We have two options. The first one, we can take actions before the flood happens, and that would be a pre-event action that is retrofitting critical network components. For example, we can choose some elements of the network, and we can improve, for example, the drainage system. Then the second option is taking actions after the flood happens. And this is a post-event action. We can have, for example, efficiently scheduling recovery resources. There have been some studies and they determined that the first option, that taking actions after the flood happens, of course, is more effective on the long run. And also, the problem with this kind of implementations are that they are more expensive and they take more time also for their implementation. That's why we decided to focus on the second approach, that is scheduling recovery resources. Of course, in an ideal world, probably many of you may be thinking, well, why not we apply the first option first? And well, in an ideal world, when everybody has like unlimited resources, that would be, of course, the best option. But given that is not the case, we are working on the second option. So what do we mean by scheduling recovery resources? It's just, in simple words, trying to select which elements of the network we should recover first, because we may have different objectives of how to recover the network. Maybe we want to reduce the revenue loss, or maybe we want to make the operability of the network be completed in less time. But also we have to consider that we are going to have some limited resources to do so. So for this, we wanted to implement reinforcement learning. Reinforcement learning, in just simple words, is trying to optimize a sequence of actions. Reinforcement learning has been applied in many fields now. For example, in large language models such as Gemini, ChatGPT, also in robotics, and also in autonomous driving vehicles. So reinforcement learning can solve problems that humans today struggle to solve. So in our case, for our problem in particular, we want to transfer all that heavy load of taking decisions from humans to machines, because humans, we have some limited information, we may have some bias in our decisions, and it can take us more time actually to take those decisions. So probably also many of you may be already wondering whether this scheduling recovery resources problem had not been already solved. But And of course, yes, there have been some previous approaches. For example, some people decided to implement static policies, that is trying to decide which elements of the network recover first based on some characteristic of the network, for example, between the centrality, or which nodes are going to be the ones that are going to be more connected to the others. Some other people also decided to use heuristics, for example, genetic algorithms. So both of these methods have already been tested and also been evaluated in terms of real-time applicability. That is how quick we can get an answer for our problem. And also both of these methods have been tested in terms of optimization effectiveness. How good are these kind of solutions? So talking about the static policies, as its name suggests, they can give you very quick solutions, but compared to heuristic, the solution they are not as effective as heuristics. The main issue with heuristics is, of course, you can have very good solutions, but the main issue is that it takes a lot of time to compute them, so they are not good for real-time applicability. So in this context, we wanted to know how reinforcement learning solutions can perform compared to these previous approaches. So talking more about the problem, we have our urban rail transportation system, or URTS. So this system is composed of stations and tracks. We can go from station to station through these tracks. These stations are going to be represented by nodes, and the tracks are going to be represented by edges. All of these elements have their own properties, and actually they also going to define how much damage they're going to receive during a flooding event. For example, that could be at grade or elevated or underground. Once we have the model for our network, imagine that we have a flash flooding event. Of course, some elements of the network are going to be affected, some others not, because it doesn't rain evenly in the whole area. And also, as I mentioned, we have these properties of the element that, of course, that is going to differentiate how much they are damaged. So having these different flooding depths, we can determine which elements of the network are going to be damaged, so how they're going to be disrupted. For example, there are some stations that are not going to be open for the public, and also some trains are not going to be able to go through some tracks. So there's going to be some discontinuation of the service. With this, we can quantify the resilience in the network. In particular, we are interested in the percentage of revenue loss. This is just comparing how much revenue we would have in the normal state of the network and damaged, compared with the damaged state of the network. So we are interested just in taking actions after the flood happens. So as you can see in the plot on the left, we are interested after what happens after the time TR. That is when the event ends and recovery begins. Our main objective here is trying to reduce post-failure impacts. And how do we do this? Is trying to deploy recovery teams effectively. So what do we mean by effectively? We want to reduce the time it takes to recover the system completely. And at the same time, we want to reduce the revenue loss as much as possible. So which recovery resources do we have in our network? We have 3 of them. The first one and the most effective one is having a team with pumps. These pumps are more effective in pumping out water, of course. But also we have the manual clean and natural receipt that are inherent to the stations. They exist already in the stations, but the problem is that we cannot use them in all cases. Imagine that we have a very completely flooded station. We are not going to manually clean it. So progressively, while we are deploying our recovery resources, these pumping teams in the network, we are going to see that progressively the network is going to be recovered. So now that we understood this basic idea, we can see our case of study. That's the London's urban rail system that is composed of many edges, tracks, nodes, stations. And of course, we are going to have also groups of them that are going to be the lines, and that also is going to determine the cascading effects in the network. So thankfully, Dr. Wei B processed all that information during her PhD. So she provided us with this information so we can continue with this study. Okay, talking about the reinforcement learning problem, we have to be able to define two things, the environment and the agent. The environment in this case is going to be the representation of the network. How is the current state of the network, how many elements are going to be damaged, and also the current deployment of the recovery teams. In the case of the agent, it's going to be represented by a policy. So the agent is going to take some actions, and this is going to affect the state of the network. Of course, some elements are going to be repaired, some not, and also that is going to be an observation for the agent. Additionally, we're going to have a reward that is going to tell us whether this action was good or bad. As I mentioned previously, reinforcement learning is just about trying to optimize a sequence of actions. So what reinforcement learning method should we use? There have been a lot of new algorithms that have been kind of proposed by many people. They have their own pros and cons, but in particular, we decided to go for a well-established reinforcement learning algorithm because of two reasons. We decided to use proximal policy optimization algorithm because it's widely used and well documented, and that helps us also for our implementation. And the second reason is because it's an offline policy training supports stable learning and generalization. I'm going to talk more about the policy and policy training in the next slide. But talking about generalization, in particular, we want to solve not only one single case of flooding event, but for many unseen cases as well. So this is a typical PPO training loop. This is just a summary. We can talk more about after maybe in the questions part. But we are going to have two main components in the PPO training loop. First, we have the actor that is going to roll the policy. The actor is going to take some actions, and this is going to interact with the environment, and the environment, of course, is going to change states of the network. Then we have a critic that is going to tell us, well, this action that the actor took was good or bad. So we're going to do this many, many times. We're going to collect a lot of experiences for many episodes, for many environments. When I say environments, for many flooding events. And then with all that experience, we can just select a mini batch of them and update our policy. Usually in PPO, and I know these equations seem a little bit difficult, but the main idea here is that we want to control how the new policy is going to be compared to the old policy. So that's why we have in the loss function clip, we have a clip function in order to control how the new policy is going to be updated compared to the old one. Then we are going to have our value function error that is going to improve how well the critic is estimating whether this action that took the agent was good or bad. Then we have our entropy bonus, that is just a function of the policy, and this is also going to help the actor to explore more the environment. So hopefully, hopefully I'm going to have more questions at the end, but probably many of you may be wondering whether this approach works or not. And it's in every computer science also algorithm that is implemented, the way you implement it is going to change the results for good or for bad. And I wanted to show also those alternatives that I tried in my algorithm. For example, for a 1,000 each year flood event, I'm showing in this slide the operability fraction, how many elements of the network are repaired over time, and also the cumulative revenue loss over time. And one architecture in particular, decided to stop repairing the elements, and we can see that the revenue loss increased over time. This is the blue line there. So it is also in these two plots, I'm comparing it with the between centrality and static approach, and also with a random policy that is just trying to select elements of the network like randomly to be repaired. So in computer science, this is pretty common depending on the approach that you take to implement your algorithm. You're going to have good or bad solutions, like our humanoid that was also trained with reinforcement learning, but it cannot reach its goal that is going to this huge sphere here in the image on the right. So, but also we had some other agents that accomplished what we wanted. They recovered the system in less time and with less revenue loss. And of course, this is very similar to what we see also in computer science. Our humanoid is able to learn to reach the goal. So also there are some interesting things that we discover. Every agent can learn different things. For example, one agent decided not to take actions every time he could, but it take actions, for example, in more time-spaced manner. Instead of deploying recovery teams at every step of time, he decided to have more available recovery teams and then deploy them. That's why we see it took like 26 decision steps to recover that complete network, of course, in longer times. And the right, we see another agent that decided to take more decisions over time, and of course recover the network faster. But of course, it's more could be computationally more expensive sometimes. So, and this is a complete behavior, unexpected behavior for us, that two agents decided to do different things. And that is also our humanoid trying to do something that we didn't expect to reach the goal. So again, this is a slide. So with the information with the experiment that we have run until now, we can see that reinforcement learning can be good at real-time applicability. Once our agent is trained, we can deploy our agent, and for a 1,000-year event, can solve the problem in just 5 minutes. But of course, we have to consider the training time. The training time is like, if I can make kind of an analogy, it's like studying for your exam for 10 hours, and then in 10 minutes, you can solve an exam. So the key takeaways, that the reinforcement learning is possible. It's a possible way of doing efficient resource scheduling with some implementation backing. As I mentioned before, the way you implement it is going to affect your results at the end of the day. The second takeaway is under the model assumptions, the approach appears computationally feasible in real-time deployment. As I mentioned, once we deploy our agent, it takes just 5 minutes to infer our result. So future directions for our research, we still have to run more experiments. There are things that we still can improve. For example, training our agent longer time. And then still we don't have the results for heuristics. So the next step also is trying to compare it with heuristics. Finally, future direction is trying to understand and ensure results. We have to interpret basically why the agent decided to take those actions. And that's it.
Thank you so much, Victor, for another wonderful presentation. And let's open it up for questions now from the audience. If anyone wants to start, if not, I have a couple questions. So when you talk about the flooding events, is it correct to say that you can describe an event fully just by the return period? Is that right? So if you say, for example, 1,000-year flood, that tells you exactly what's going to happen for that event.
Yeah, these studies are made by hydrological institutes. Actually, the information that we got were in particular for London. And of course, they have their own way to compute the 1,000-year flood scenario. But of course, due to climate change, this is going to be also subjected to change.
Okay. Okay. And the idea is that you have a policy specific for that return period, right? Like telling you where to deploy the pumps and so on for example, a 100-year event or a 1,000-year event.
Yes, of course, depending on the return period of the event, we are going to have more elements or more nodes that are going to be damaged. In particular, for this approach, we decided to implement a simulator. The simulator is going to generate different events that can, for example, you can decide how many elements of the network are going to be damaged, and that can be randomly as well.
Okay. Okay. Thank you.
Thanks to you.
Are there any other questions, Jürgen?
Yeah, I can ask one question. So it seems like to get good results, it's very case specific. How do you think about making it more generalizable? It seems like they're going a lot into this hyperparameter tuning, setting up the right architecture. And I guess people want to have something which works fast out of the box without thinking too much. So how would you bridge this gap, or where you see the way forward to approaching this more universal application of this kind of tools?
The application, I think that in particular in our area in civil engineering, it's so limited because of two reasons. First, because it's still new. Deep reinforcement learning, machine learning algorithms are quite new. So, and there's still a lot of interpretability work to do. So, for example, deep networks, this is well embedded in deep reinforcement learning, but they're still kind of a black box. So, as I mentioned, and actually part of my future directions work is trying to understand why this agent decided to take these actions. Regarding, for example, whether we should implement more things or have more trials, for example, to get a solution. And this is what people in computer science do. It's kind of course, we are going to have a lot of errors, and that's also what happens in engineering. But of course, there is kind of, for now, as we cannot interpret things sometimes, we cannot say, well, this is going to be the 100% approach, best approach that we can have. So we have to have many trials, and in particular for very new problems like this, where we have a network and we have to learn different things compared to an image or a video, something that we already have in ChatGPT or Gemini. Well, we have to consider some other aspects also of the network that may give us different results. Hopefully I could answer the question.
Somehow, I guess the question was more like, no, you have your example here with this lab, with this maze, and I think similar is what you have now with this network for London. But the question would be, how can someone in New York use your approach? Do they have to retrain it, or how do you transfer this information to other networks, since it's very particular tuned now to the London Tube network?
Oh yeah, that's another question that I also have been asking myself. Some people, for example, for generation of images, something that you can have now in ChatGPT, use, for example, patterns during the training process of course, the neural network. And these patterns can be shared not only to identify things, but could be also identify videos and images. But the thing is that probably a similar approach could be implemented in networks. We can get during the training process some patterns of the networks that we can also share to other networks as well. But also that's pretty new. That could be also implemented to networks as well.
So out of curiosity also, have you tried comparing the results you get, I guess in terms of revenue that you save, comparing this approach to, say, like a dumber approach, like saying, for example, I don't know, deploying the pumps to the stations that have the most traffic or something like that, and seeing how that affects the savings, time savings or
Okay.
revenue.
That also could be done. That is kind of making a masking of the actions, deciding which elements we should recover first. There could be two different approaches here. According to, well, the fathers of reinforcement learning, they say, Sudo and Barton, they said, you have to just give the agent your reward function, and then the agent has to figure out by itself which are the best actions to take, which elements should be recovered first. It doesn't matter if they have more between centrality or they have more demand at each moment, but just they want to get more rewards. In this case, our reward function was shaped just to reduce the revenue loss. That was our main objective. The second approach, apart from the reward, is, as I mentioned, we can mask the action space and say, well, we should focus more on certain elements, for example, the edges and certain particular edges of in London's downtown part area, and just focus on those, and let's see how it goes if it recover them first. But also, yeah, there are many approaches that we can take here. We haven't tried them. Also, that would be another step during the research. But for now, we just focus on the revenue loss.
Okay, thank you. Are there any other questions for Victor? If not, thank you, Victor, once again for an amazing presentation. Thank you, Muhammad, as well. And with that, we conclude our session for today. I want to thank you all also for being here today and for participating. And I look forward to seeing you all on our next session next month.